Okay, so we're talking about 4.3, what derivatives tell us about the shape of a graph. And here's a summary of everything. First one is the increasing decreasing test. This comes from the mean value theorem. It's a result of the mean value theorem. And I talked a little bit about this last time. Okay, if the derivative is positive on an interval, then the function is increasing on that interval. If it's negative on an interval, then the function is decreasing on that interval. If you have a situation, so let's take a look at the first one. If f changes from positive to negative at c, then it's a local maximum. And the reason for that is, let's say this is c. If your derivative is positive, that means you're increasing. And then if your derivative is negative, that means you're decreasing. So this point here has to be a local maximum. So the derivative is positive here, and then afterwards negative. The second one, if it goes from negative to positive, then what you're going to have is a local minimum. So the derivative negative and then positive after, that's going to be a local minimum. And if it's positive to the left and right and negative to the left and right, then there's no local maximum or minimum. Okay, so this is when you already have a critical number. So this situation right here would be where you're coming up like that, and then you just continue to go up. Okay, so maybe the derivative is 0 there, which makes it a critical number, but it's not a local minimum or maximum because the derivative is positive here and then positive over there. Okay, and then of course, and then this other situation is where you have negative, and so maybe it's going like that. Okay. It's down like that and like that, or it could be a situation where your critical number could be because the derivative doesn't exist. Okay, that could happen too. Okay, but then it's not a local minimum or maximum because the derivative is negative and then negative after. Okay, the next one is the second derivative. Okay, which determines what's called concavity. If the second derivative is positive, okay, so the second derivative being positive means, if you look at it from this point of view, it means that the first derivative is increasing. Okay, so if the second derivative is positive, then the first derivative is increasing. Okay, and it's called concave up. So concave up would be something like this. This is a situation where you have concave up. And then if you go if you come over here, then over here, this is concave down. You see how the graph's kind of curving? So here, for example, it's decreasing, but the rate of decrease is slowing down. And here it's increasing, but the rate of increasing is going up. Okay, so that's concave up. And then it changes right here. And then it's concave down. And this point right here would be an inflection point where it changes from going concave up to concave down. Okay, so you can kind of see, another way to look at it is if you were to cup your handle in this shape, then maybe you could hold a little bit of water there. Okay, but if you're like this, then the water wouldn't collect at the top there, it would fall down. Okay, so that's kind of another way to look at it. So that the second derivative is negative, then you're concave down. Okay, so right here, this is where the second derivative would be positive, and here would be the second derivative is negative right there. Okay, now if the first derivative is 0 and the second derivative is positive, then you have a local maximum, the local minimum, I mean. So if you're like this, for example, your second derivative is negative, right? And your first derivative is 0. So that means that would be a local maximum. Okay, so that would be the local maximum. And then the second one where your second derivative is positive, okay, and your first derivative is 0. Okay, and that would be a local minimum. Okay, so if the second derivative is positive, but you also have to have, again, you also have to have these, you also have this condition right here. You have to be actually be a critical number. Okay, so these are some tests that you can apply. The first derivative test is probably more conclusive because sometimes you'll have weird things where the first derivative will be 0 and the second derivative will be 0. And so then you're like, okay, what's that? And sometimes that means that you're in this last situation, but sometimes it's a local maximum or a local minimum, or sometimes it's neither. Okay, if you have this being 0 and the second derivative being 0. Okay, so let's get to the homework. Hopefully that's a little bit of an introduction there. So first exercise, consider the following graph. Find the intervals on which the f is increasing. So this is the graph of y equals f of x. Now they're a little bit tricky in this section because they're going to give some graphs. Sometimes they're going to show you the graph of the derivative, and when they do that, then you have to realize that that's the derivative, not the actual function, and so then you have to act accordingly. We'll get to that though, and try to work our way through that. Okay, so where it's increasing. Okay, so it's increasing from 1 to 3. And notice that the first derivative is positive, but it's also increasing from 4 to 6. Okay, so that would be the good answer for the first one. Where is it decreasing? Okay, so 1 to 3 and 4 to 6 is where it's increasing. And then it's decreasing from 0 to 1 and then 3 to 4. 0 to 1 and then 3 to 4. Okay, so when it's asking where we're finding intervals, it's asking for the x values, not the y values. Because if it was said, if this was stocks, you might say, okay, it decreased from 5 to 2. Well, yeah, but it's on the first hour of the day, it was decreasing. Is probably the best way to do it. Okay, find the open interval on which f is concave upward. Okay, so right here, it's concave upward. It shifts right there at that point right there. Okay, so here it's concave upward. Here it's concave down. Here it's surprisingly, it's also concave down. Okay. But this is where it changes. So 0 to 2 would be where it's concave upward. And then it's concave downward from here to here, it's all concave downward, and then from here to here, but not at that point there. So let's see, 2 to 4. At that point, it's like it's just not even the second derivative doesn't exist. So you have to do that. And then the points of inflection. Okay, that is this point right here that we talked about, and it's 2, 3. Okay, let's move along to the next exercise. Number 2, suppose you are given a formula for a function f. How do you determine where f is increasing or decreasing? Okay, we talked about that before. If the first derivative is, increasing means that the first derivative is positive. Okay, decreasing means the first derivative is negative or less than 0. Greater than 0, less than 0. And how do you determine if it's concave upward or downward? Okay, upward means that the second derivative is positive or greater than 0. Downward means that the second derivative is negative. Okay, how do you locate inflection points? Okay, so an inflection point, now let me make one thing clear. An inflection point is not necessarily where the second derivative is 0, okay? Because you could have the second derivative being 0 and it not be an inflection point, okay? Or you could have the second derivative not exist and it could be an inflection point, okay? So let me just clear that up right now. It's where it changes concavity, okay? So let's look for it changing concavity. Okay, at any value, so it's this last one right here. At any value of x where the concavity changes, that is what makes it an inflection point. Okay, where any value of x where the concavity changes, where it's going from concave down to concave up, or concave up to concave down, that's an inflection point. And a good way to find those is where the second derivative is 0 or where the second derivative doesn't exist. But that doesn't necessarily, just like the first derivative being 0 doesn't necessarily, or having a critical number doesn't necessarily mean that your function is going to be, is going to have a local maximum or minimum. Okay, number 3, the graph of the derivative. Okay, this is the graph of the derivative, not the original function, okay? So this is the graph of the derivative. So you have to like keep that in mind. Okay, so part A, on what intervals is f increasing? Okay, so now here, it's increasing when the first derivative is greater than 0. Okay, so that's why it's going to be from 0 to 1. It looks kind of weird because you'll be like, whoa, the graph is going down. Okay. But what you want to look for in this graph right here, this is the derivative, it's not the actual function. What you want to look for is if it's above the x-axis, okay, above the x-axis, that's where it's going to be positive. And then over here from, so here, and then from over here from 3 to 5. Okay, and then where it's decreasing, so decreasing, that would be f prime where f prime is negative, and that would be below the x-axis. Okay, and that's going to happen from 1 to 3, and then from 5 to 6. Okay, what values of x does f have a local maximum or local minimum? Okay, so now here we're going to the first derivative test. So if you think about right here, so here the derivative is positive. Here the derivative is negative. Okay, so if the derivative goes from being positive to negative, that means that the function was increasing, and then it leveled out, and then the function was decreasing. Okay, so that's going to be a local, so this right here, this number 1, that's going to be a local maximum. Okay, because you went from increasing to decreasing. Here at 3, your function is decreasing, and then over here it's increasing. Okay, so that's a minimum. And then over here at 5, it's going to be another maximum. Okay, but all they want is the x value, so that's fine. Okay, if there's any questions, just let me know, please. Okay, number 4, we have the equation here, x to the 4th minus 32x squared plus 1. Find the interval where f is increasing and then where it's decreasing. Okay, so what you want to do here is calculate the first derivative. Okay, so that's going to be 4x cubed minus 64x. Okay, first of all, we're going to figure out where that's 0. So I'll factor 4x out, and that's x squared minus 16. So completely factor would be x minus 4x plus 4. Okay, so that gives us, I'm going to make a little chart here because I like to be straightforward about these things. So 0, make a chart here with all the values. I think I might have showed you how doing this before, but this is something you're going to do a lot. Okay, so there's the factors here are 4x, x minus 4, and x plus 4. Okay, so 4x is negative here and here, but when you cross over this point, it becomes positive. Okay, x minus 4 is negative here and here and here. It crosses over where it's 0. It's 0 here, so over here it's positive. And then this one is negative here, but it's 0 here, and so it becomes positive there and there. Okay, now f prime of x, which is the product of all of these three terms, that's going to be the product of three negative numbers. That's negative. It'll be positive here because two negatives and a positive. It'll be negative there, and it'll be positive there. Okay, so where it's increasing will be this interval, negative 4 to 0, and this interval here, 4 to infinity. And it'll be decreasing from negative infinity to negative 4, union 0 to 4. Okay, so this interval and this interval. Okay, local maximum value and minimum values. Okay, so for this one, we have to think, okay, the function is decreasing, and then it's increasing here. So there will be a minimum here. It's increasing and then decreasing, so this will be a maximum, a local maximum. And there'll be a local minimum here. Okay, so it's increase and a decreasing and then increasing local minimum. Increasing and then decreasing local maximum. Decreasing, increasing, so that's the local minimum. Okay, so we have those right. So there's going to be two right numbers here. Well, maybe not. And the one number, there could be just not one number. Okay, so when it's asking, what it's asking for here is what is the y value. Okay, it's not asking for where the local maximum or minimum occurs. It's asking for what is it? What number is it? So that would be the y value is what they're asking for. Okay, so what that means is you're going to take this f of negative 4 and calculate that. Okay, and that turns out to be negative 255. Okay, f of 4 is also negative 255. Okay, so both of those numbers come from that. And so we're just going to put, those are local minimums, so negative 255. And then f of 0 is, you can just plug it into here. That's just going to be 1. Okay, so that's just a 1 right there. Okay, part C, find the inflection points. Okay, so what we need to do here, and then it's going to ask for its concave up and concave down. So for that one, we need to take the second derivative. So we will go ahead and take the second derivative right here. So just differentiating this, that's going to be 12 x squared minus 64. Okay, and we'll go ahead and set that equal to 0. You can factor a 4 out. And then I'm going to factor this further. It's going to look kind of weird, but the square root of, the square root of 3x minus 4, and then the square root of 3x plus 4. And this gives you 4 over the square root of 3. This gives you negative 4 over the square root of 3. Okay, and so I'm going to go ahead and do a little chart here. because we want to find out what the sign of this is. So we have, the factors are 4, and then there's this one, root 3x minus 4, and then root 3x plus 4. Okay. Okay, that's always positive. I mean, probably didn't even need to write that down. Although, you know, the danger of not doing this is if this is negative on the front and then you just like ignore that, then that you should have negatives all across. But if you just don't put it down, then you could potentially get everything wrong. Okay, this one is negative here, and then it's still negative there, and then positive. And this one is negative, and then because it has the plus 4, then it becomes positive sooner. And then the second derivative, which is the product of these three, is going to be positive there, negative there, and positive there. Okay, so that means it'll be concave up here from negative infinity up to -4 over the square root of 3. Union, okay, that's positive there, and then positive over here from 4 over the square root of 3 up to infinity. Okay, and then of course in the middle it'll be concave down from -4 over the square root of 3 to 4 over the square root of 3. And then finally, the last thing that they wanted is the inflection points. And concavity changed right here and right there. Okay, so the first inflection point is going to be when your x value was -4 over the square root of 3. And your second inflection point would be where you have 4 over the square root of 3. Okay, but those are just the y values that want an ordered pair. To get that, you have to go back to the original function. Okay, and so f of -4 over root 3, ouch. So this is going to be -4 over root 3 to the 4th power minus 32 times -4 over root 3 squared plus 1, and that is, I calculated it, fortunately, so that's -1271 over 9. Okay, so that's what's going to go there. And f of 4 over the square root of 3 is also going to be that because it's being right, this is raised to the 4th power here, so they became positive, okay? And then this is just the negative of that one, so it's also -1271 over 9. Okay, so that's the thing. You plug it back into the original function, not into the second derivative or anything. Okay, great. That was quite involved. Okay, let's move on to number 5. Ooh, ouch, we have another word function. So the same thing as last time, except our function is x to the 7th log x. So let's go ahead. So the first derivative, okay, it's the product rule. So it's the derivative of this one, which is 7x to the 6th times log x, plus the first one times the derivative of the second one. The derivative of log x is 1 over x. Okay, so you're going to get 7x to the 6th log x plus x to the 6th. And I can factor a x to the 6th out. I want to set that equal to 0. I'll factor an x to the 6th out. That gives me 7 log x plus 1 equals 0. Okay, if we take this 7 log x plus 1 and we set it equal to 0, okay, so set the second one equal to 0, then we'll have this. And then we'll have log of x equals -1 over 7, and so x will be e to the -1 over 7. Okay, because e exponential function e to the x is the inverse of the natural log of x. So that's where it's 0. And then I can do my little chart here. So it's 0 here. And it's also 0 at e to the negative 1 over 7. Okay. So notice that that's negative, but this is positive. So x is actually positive. This is actually 0 where x is a positive number. Also, we're also running into some domain issues. Okay. So we're also running into some domain issues. It's not defined when x is less than 0. This function is not defined when x is less than or equal to 0. Okay, it's just not defined there. So we have to remember that when we go to write our answers down. Okay, so let's go ahead and we got x to the 6th, and we have 7 log x plus 1. Those are the factors of f prime. X to the 6th is always positive no matter what. This one is negative here and then positive after, because this is 0 here. Log x is an increasing function, so it's going to be negative over here and then positive after. Okay, that means the first derivative will be negative there and positive there. So increasing on this interval from e to the negative 1 over 7 to infinity, decreasing on this interval, okay, from 0 to e to the negative 1 over 7. Okay, local minimum value. Okay, it's decreasing here and then increasing. That means that it will have a local minimum value here. Okay, so this will be local minimum, not this number. Again, you're going to have to find the x. You're going to have to put it into here. Okay, so that means that we put e to the negative 1 over 7 in here. And that's raised to the 7th power times the natural log of e to the negative 1 over 7. This is going to be e to the negative 1. And then this is going to be negative 1/7. So it's negative 1 over 7e. Okay, that'll be the local minimum value, negative 1 over 7e. Okay, local maximum. There isn't going to be one, so this does not exist. Okay, because this is the only critical number that's interior. This, maybe you could call this a critical number, but no, it's not interior, so it doesn't really count because that's at the edge of the domain. Okay, inflection point. Whoa. Okay, so now for the inflection point, what you want to do is find the second derivative. Okay, so let me start with, I'll take it from here. I'll take the derivative of this, and that will give me the second derivative. Okay, so this is going to be product rule. So the derivative of this, I'll bring the 6 down. So that's going to be 42 x to the 5th log x plus this 7x to the 6th times the derivative of log x, which is 1 over x. So the derivative of this is that. And then the derivative of this is 6x to the 5th. Okay, so I'm going to go ahead and set that equal to 0 because I want to find out where it's 0. So let's see here. Let's see what we got. This is 42 x to the 5th log x. This is going to be 7 x to the 5th and then 6x to the 5th. Okay. I can factor x to the 5th out of everything. And that leaves me with 42 log x plus, and this is going to be 13x to the fifth. X to the fifth comes out, and I just left with the 13. Okay, so that's going to be 0 where the second part is 0. Okay, so 42 log, I guess I could do it here, 42 log x is negative 13, which means that log x would be negative 13 over 42. And so that's going to give us x equals e to the negative 13 over 42. We get some weird numbers in this class. Okay, so negative 13 over 42. Okay. And now what we're going to do is we're going to go ahead and set up this right here, x to the fifth, and then 42 log x plus 13. And then we have the number line. And of course, we have 0 where there's nothing right here. And then we have this e to the negative 13 over 42. X to the fifth is always positive. This is negative here and positive there. So that means you're concave down on this interval. And concave up on this interval. Okay, so maybe I should color code this. So here you're concave down. And so that would be 0 to e to the negative 13 over 42. And here, on this other one, we're concave up. So that would be e to the negative 13 over 42 to infinity. And then it changed concavity here. There's no other place where it changed concavity. It changed at that point. So you want the inflection point. The x coordinate of the inflection point will be e to the negative 13 over 42. Okay, the y coordinate, ooh, that's tricky. Okay, for the y coordinate, we plug it into the original function. So f of e to the negative 13 over 42. You have to plug it into here. So it's going to be e to the negative 13 over 42, all raised to the 7th power times the natural log of e to the negative 13 over 42. This is going to be e to the negative 13 over 6, because 42 divided. Okay, so the 7 just comes in here, and then 7 reduces this. The 42 divided by 7 is 6, so it's negative 13 over 6. So the y, and then this part right here is going to be negative 13 over 42. Okay, so this is going to be negative 13 over 42 e to the negative 13 over 6. Okay, great. Any questions on that? Okay, let's work on the next exercise. We have this weird function, x to the 4th times x minus 3 to the 3rd power. So find the critical numbers of the function. So go ahead and take the first derivative. Okay, so derivative of the first part, which is 4x cubed, times the second part, plus the first part times the derivative of the second part. Okay, so derivative of that is bring the 3 down, it reduces to a 2, and then this one is just 4x cubed. Okay, now, so we're going to set that equal to 0, and those are going to be our possible, those are going to be all our possible, all the solutions to this will be all the critical numbers. Okay, so out of everything, I can factor an x cubed and an x minus 3 squared. Okay, so I'm just going to factor it out. Maybe I should little bit more. I can factor in x cubed, and I can factor in x minus 3 squared. Okay, now, what's left over from here will be 4 and an x minus 3. What's left over here will be an x and a 3, well, 3x. Okay? And then I'm going to go ahead. This is 4x minus 12 is all that. And so then I end up with this x cubed times x minus 3 squared times 7x minus 12. And this gives me 0. That gives me 3. This gives me 12 over 7. So just put that the smallest one is 0. That's the smallest of these three. This is the next smallest, 12 over 7. And this is the largest, 3. Okay, what does the second derivative test tell you about the behavior of f at these critical numbers? Okay, so now, we gotta take the second derivative. Boo. Okay, let's take the second derivative. Let's do that over here. Okay, let's take the derivative of this. So when you have three things and you want to apply the product rule, then you take the derivative of the first one times all the other ones. Plus the derivative of the second one times all the other ones. Plus the derivative of the third one times all the other ones. The derivative of the third one is just 7. Set that equal to 0. Okay, so now I'm going to factor out it looks like I can get an x squared and then x minus 3. Yeah, looks like about it. Okay. Because every term has that. So if I take an x squared and x minus 3 out of here, I end up with and I end up here, I end up with 2x, that's gone. And then I have a 7x, x minus 3. Dang, I hope I didn't make any mistakes. If you see any mistakes, please let me know, because then let's see, that means that's gone, this reduces, this reduces, this reduces, that reduces. Okay, that looks okay. I think maybe we actually, I think we have enough information. We have enough information. No need to quote simplify this anymore. Okay, so at x1, when x is 0, this is 0. Everything goes away. Okay, so the second derivative at 0 is 0. Also, the second derivative at x3, which is 3, is also 0 because this is 0. This one right here zeroes everything out. Okay, because you have 0 times all this other stuff. So that means that this is inconclusive. This is inconclusive too. Okay, now this one, yeah, we don't, I apologize, you don't need to set this equal to 0, by the way. Okay. Okay, at this 12 over 7, that's that. This is 12 over 7 minus 3. That, and then this is going to be 0, and that's also going to be 0, because when you put 12 over 7, this is 0, and that's 0. And then over here, you're going to get 7 times 12 over 7 times 12 over 7 minus 3. Which, this is negative, that's positive, this is negative. So that's going to be greater than 0. Okay, so the second derivative at 12 over 7 is greater than 0. So that means you have a local minimum. Because the second derivative is positive, so that's a local minimum. Okay. Part C, what does the first derivative test tell you? Okay, so for that one, so for the first derivative test, what you want to do is you want to look back to this right here. And I'm going to go ahead and lay this out right here. So I have the smallest one, 0. Then I have 12 over 7, and then I have 3. And then all the factors are x cubed, x minus 3 squared, and 7x minus 12. Okay, this is negative here and positive there and there. This one, it's squared, so it's positive everywhere. This one is negative here, negative there. It's 0 here, so it switches right there. So positive, positive. Okay, so the first derivative will be positive here, negative there, positive here, and positive there. Okay, so the derivative is positive and then negative. That means this is a local maximum. Because we have positive to negative. At this point, we went from negative to positive. So that's a local minimum. Okay, and then positive to positive. That means it's neither a local minimum nor a local maximum. Okay, so what happened here? The first derivative test gives you more information, or it could give you information that the second derivative test doesn't give you. Okay, because so like this first one, the second derivative test was inconclusive, meaning it could go either way. But the first derivative test tells us this is a local maximum. Okay. Here they both give the same result. Of course, they're gonna if they're giving a result, then it's going to be the same result. On this third one, this is inconclusive. This is telling you that it's not a local minimum nor a local maximum. That's what that's telling you. Okay, good. So let's move on to number 7. And what we have here is a bunch of conditions. Here we want the first derivative and the second derivative. Oh, wait, the first derivative is 0, 2, and 4. So 0, 2. So let's do this one. 0, 0, 2, and 4. So those are all fine. You want those derivatives to, oh, whoa, at 4 it's not 0. So this is out. Because at 4 it doesn't work. Okay, 0, 2, and 4. Those are fine. Okay, the next condition is we want the first derivative to be positive if x is negative, and we want it to and between 2 and 4. So in here we're fine, and then between 2 and 4 it's negative. Yeah, so they're decreasing there and there. Here it's increasing, so this one is out. And it's increasing there, so that's out too. So this is out. And then let's see, what do we got here? it's, wait a minute, what am I doing? I am just saying the total opposite of what's happening here. This is decreasing. This is decreasing, and that's decreasing there. It should be increasing. Like this. This is fine. That's good. This is good. That's good. Okay, this next one. Decreasing from 0 to 2 is decreasing. And by the way, that's out. From 0 to 2, yeah, that's fine. And from greater than 4. From 0 to 2 and greater than 4. Well, right here, maybe not. I don't know. It looks like, I think it looks like this is gonna, I think this is just, oh, maybe, I'm not sure. Because this looks like 0 right here. But let's just check out the next thing now. The second derivative is positive, so this is concave up from 1 to 3. Let's see, from 1, this would be from 1 to 3. Yeah, that looks concave up. And then here, yeah, that looks concave up as well. And then concave down from less than 1 and greater than 3. Yeah. Oh, no, it's concave up here. So that doesn't work. This is concave up. So it's going to be this one. Yay, this one right here. Dang, we're running low on time. We still have a bunch more problems left to go. Number 8. Okay, this is the graph of the derivative. So you have to remember, this is the graph of the derivative. Okay, so on what intervals is f increasing? Okay, so this is the derivative of the integral. That means you're looking for above the x-axis. Okay, so from 1 to 6, and from 8 to 9. It says assume f prime continues to infinity. I'm not sure what that means, but it doesn't mean that apparently it doesn't mean to put an infinity right there, because I tried that and it was wrong. So 8 to 9 works though. And what intervals is it decreasing? This would be below the x-axis, which is from 0 to 1 and from 6 to 8. Okay, at what values of x does f have a local maximum? Oh, that's great. So we can just pick that off. Wait, no, we can't. So here it's, so for local maximum, you're looking for positive to negative. Okay, so here it's positive. Here it's negative to positive. No. Okay, so here it's positive, negative. So positive to negative. So it's 6. Okay, is the only one. And then local minimum, that would be negative to positive. So negative to positive happens here at 1 and also at 8. Okay, and what intervals is f concave upward? Okay, so the concavity is the second derivative. And so f prime is increasing. So where it's increasing. So it's increasing from 0 to 2. And also from, we'll say that's 3 to 5. And from 7, we'll say that's 7 to 9. That's where it's increasing. And then third one is you want that where the derivative is decreasing. And that's going to be from 2 to 3, and from 5 to 7. Okay, so from 5 to 7. Okay, and then part D is the x coordinates of the points of inflection. And these will just be the endpoints here. So 2, 3, 5, and 7. And then the next part was to sketch a graph of it. Okay, so here is the derivative, and we want this to be f. So this is f, and this is f prime. Okay, so let's see here. How to figure this out. Let's look at things here. I mean, I guess we could look at everything that we did on the previous page, but there wasn't enough room to fit it all on one page. So now let's just start over from scratch. Okay, so it's decreasing from 0 to 1. We'll look for a function that's decreasing from 0 to 1. That's not. That one is. That one is. That's not. Well, so we eliminated those two already. Okay, it's increasing from 1 to 7. I'm sorry, 1 to 6. So from 1, that's already out. What is that? So from 1 to 7, it's what? From 1 to 7, it's in. No, from 1 to 6. I'm sorry. From 1 to 6, it's increasing, and that looks okay. This one, no, because it goes down right there. So it's got to be the second one. Okay, so I would probably spend more time explaining that, but we're kind of low on time. So let's go to the next one. So at number 9, consider the function, find the intervals of increase. So here we have another function. This is the original function. So let's take you had to take the derivative. So the derivative of that part is 9 x plus 1 to the 8th minus 9. Okay, now I can set that equal to 0. This is kind of interesting because I can factor a 9 out. And let's see, what kind of logic can we use here? Okay, so you're looking where this is. This depends on where this is greater than 1 or less than 1. So this is the same as looking at like this. I guess you could say equals 0. And I guess, well, let's do this one here. Let's do this. Intervals of increase. Okay, so that increase would be where this is greater than 0. And it depends on whether this is greater than 1 or not, which is the same as this being greater than 1. Okay, so, and then this one splits up into 2 pieces, either less than -1 or that's greater than 1. So this would be x less than -2 or x greater than 0. Okay, so that's going to be from -infinity to -2 union 0 to infinity. And then everywhere else it's going to be decreasing. So from -2 to 0. Now for this one again, we could just go like this. And then that gives us that. So -2 to 0. Find the local minimum value. Okay, so we can kind of construct here what's going on. So at -2 and 0, that's where the action is. It is the first derivative is positive here, negative there, and positive here. So for local minimum values, you're going from positive to negative, which is going to be right here at 2, at -2. Okay, so dang it, my colors are all over the place now. And let's do this right here. So what you're going to do is you're going to calculate f of -2, which is -1. Is it? No. I got mixed up. I'm just rushing it and I got mixed up. So this is actually maximum is plus to negative. And so that's going to be where the maximum is. That's where the maximum is. So the value is going to be the value at -2, which plug all that stuff in, and you get 15. Okay, so that's going to be 15. Now, this one, we're looking at okay, so for part B, we're looking at negative to positive. So that would be f of 0 would be 0 right here. So you put a 0 in here, you get 1 minus, so you get -1. Okay. And then for the inflection point, here we take the second derivative. We got the first derivative right here. The second derivative, you have an 8 come down. So 8 times 9 is what? 72. X plus 1 to the 7th. And then this goes away. Okay. So at -1, you're going to have an inflection point. So -1, comma, and then put that in here. H of -1 is equal to 7. So 7, you put -1 here, that goes away, and you have -1 here, that's going to be +9 minus 2, that's 7. Okay, so find the intervals where it's concave upward. Okay, so that's going to be from -1 to infinity. And then concave downward will be from -infinity to -1, because it changes right here at -1. And then sketching the graph. Sketching the graph. So it's increasing from -infinity to -2. Yeah, that's increasing there. And decreasing from, oh, and also from 0 to infinity and decreasing in between. So that's good. This one's not good because that's decreasing. This one's not good because that's decreasing. This one looks okay too. Okay, so those two are eliminated. Now, it looks like these pretty much have the same shape, except, wait a minute, what am I thinking? No, this is way off, because -infinity to -2 would be up to here, and then it's supposed to be decreasing here. So this is the only one that it could be. Okay, we got just one more problem to go, and then we'll be done, I promise. So let F of T be the temperature where you live, and suppose T equals 4, you feel uncomfortably hot. This is nothing you do with the problem, absolutely nothing you do with the problem. What happens to the temperature in each case? Okay. So the derivative at 4 is -1. That means that the temperature is decreasing. And the rate of decrease is becoming more negative. Okay, so that will be this one. So the first derivative means the temperature is decreasing, and then the rate of change is decreasing. Here, the temperature is decreasing, but the rate of change is increasing. So that would be this one. Here, the temperature is increasing, but the rate is decreasing. Okay, so that'll be this one. And here, they're both increasing. The temperature is increasing, and the rate of increase is also increasing. Because this is positive, positive, this is positive, negative, this is negative, positive, and those determine which one it is.